Hello and welcome to this short popular science presentation on the supergrid linear eddy model. My name is Abhilash Menon and I shall talk about this method for simulating combustion and fluid dynamics that was developed during my PhD project at Chalmers University. In this presentation, I shall give a brief introduction to simulation and how it's used in modern engineering, fluid simulation and CFD, or computational fluid dynamics, the simulation of combustion, also known as reactive flow simulation, a particular model known as the linear eddy model, or LEM, which forms a backbone to this work and is a predecessor to the current work. Next, I'll describe a new version of LEM known as supergrid LEM or SG-LEM that was developed during my PhD, the motivation behind it and how it works. And finally, we conclude with some achievements and future work. Let's begin with simulation. Simulation plays a very important role in modern engineering design cycles. The main use of it being to check various aspects of a design before it enters the prototyping or production phase. For example, we can simulate the air flowing around a car and how this will be affected by various design changes, thereby affecting its real-world performance. An advantage being that we can generate rather detailed data. The example shown here is how air moves through the wheels of a car, perhaps cooling the brake pads. This is done alongside testing in a wind tunnel, but it can be a lot cheaper to generate the same amount of data and detail. Some more examples of simulation. We can estimate how a bridge section would deform and vibrate. Virtual crash testing, which you can imagine can be done multiple times at various speeds and angles, which is cheaper than running several real crash tests. We can simulate how the flame behaves in an internal combustion engine, and also various other aspects like fuel sprays and mixing of air and fuel. And this example of a rather detailed simulation of a gas turbine. These last two examples are typical use cases for combustion CFD. So what does combustion simulation entail? It's a branch of CFD or computational fluid dynamics. It also involves a simulation of chemistry or how the air and fuel molecules react to produce heat, burn products like carbon dioxide, and pollutants such as NOx and carbon monoxide. Other aspects can include the simulation of fuel sprays like those made by an injector in a diesel engine, or how the flame can heat up components like the cylinder walls in an engine. Combustion CFD forms the background area for this work. It's an interplay between fluid flow, or the movement and mixing of air and fuel, turbulence, the example shown here is the small turbulent structures you see when you mix milk and coffee. Similar structures are present in the air around us and in devices like engines, and finally, the chemical reactions that produce heat. These three components influence each other to produce a dynamic flame. A major challenge here is the separation of scales from large-scale fluid movement, small-scale turbulence, and diffusion in chemistry happening at the molecular scales. Let's briefly touch upon CFD and why challenges arise when simulating combustion. First, we need a computational grid, or mesh. For example, if you were to simulate the airflow around this motorbike, we need to first divide the space into small chunks known as finite volumes or simply cells. Together, they form the grid. When we run simulations, we obtain data for each cell, as seen in this figure. Here, each cell contains data such as velocity, pressure, kinetic energy, etc. Structures that are smaller than the grid cells cannot be directly simulated. These are the unresolved scales. We could use higher resolutions to get more accurate data, but that results in slower simulations or higher compute demands. Resolving all the scales, even the smaller scales, is known as direct numerical simulation, or DNS. So far, this is impossible for practical simulations such as motorbike. For combustion, this presents a problem. Flame fronts can be much smaller than the grid size delta. A flame front, as depicted here, is a thin reaction zone where the air-fuel mixture undergoes chemical reactions to form hot burn products such as carbon dioxide and water. Secondly, small turbulent vortexes known as eddies that are smaller than delta can also disturb and wrinkle these flame fronts. Reactions themselves are molecular phenomena and no practical grid can resolve such small scales. Over the years, a lot of research has gone into resolving these issues, which has resulted in many widely used methods. We shall focus on one such method known as the linear eddy model, or LEM. When using LEM for CFD, we first begin with a CFD grid of resolution delta, and then we embed each cell with a 1D domain, which has an even finer resolution. These are called LEM domains or LEM lines. We then simulate flame fronts on these embedded LEM domains. This is much more affordable than resolving in all 3 dimensions. LEM lines can simulate flames, particularly heat diffusion and chemistry. But they can also simulate the small eddies using something called triplet map rearrangements. Let's see how we can simulate a single turbulent eddy or vortex. If we start with the LEM in this state with cells numbered 1 through 9, a single triplet map results in the shuffling of LEM cells as seen by the numbers below. This is how eddies are simulated in LEM. Here we see an example of two 1D flames. The blue line is undisturbed by eddies, while the black line shows how eddies influence the flame speed. When CFD simulates the large-scale fluid motions, this flow of material and information is transferred to the LEM domains through a process known as splicing. For example, if we assume a flow in this direction, we can simulate that by first breaking the LEM domain into small fragments and then attaching these fragments to neighboring domains. Likewise, fragments arrive from other neighbors that bring material and information from those neighbors. So what's the problem here? LEM is still a very expensive method despite its many plus points. The reason being that chemistry must be simulated for each LEM cell. Hence, if there are many LEM lines in our simulation and many LEM cells, the simulation becomes very expensive and slow. Also, chemistry computation can be rather tedious as combustion can involve rather many chemical reactions. Finally, we arrive at the method developed during my project to improve compute times. First, we perform a clustering of the CFD cells, as shown by these dark lines. This results in a coarse-level supergrid. We then embed each cluster with an LEM line, instead of the picture on the left where each grid cell has an LEM line. This results in fewer LEM domains, fewer LEM cells, and thus much faster simulations. The next step is to obtain data for each member of the cluster. For this, we used a statistical method that was developed known as the mapping procedure. In other words, we are able to reconstruct high-resolution CFD data from the LEM lines that are embedded in the low-resolution supergrid. Let's look at some results. This is a flame case known as the Volvo validation rig. Here, there's an air-fuel mixture moving from the left to the right, and the flame is being stabilized behind this triangular flame holder. The supergrid panels shown here and here show us what's happening inside each cluster as the embedded LEM domains are evolving the flame solution. The panel on top being temperature and the panel in the middle showing carbon monoxide. The mapping procedure shown by these two arrows is what gives us the high resolution CFD data. This mapping includes temperature, density, species concentrations, species such as carbon monoxide, and other data as well. In turn, the CFD, as it evolves velocity, will feed back to the supergrid via splicing. Splicing, to recap, is how the flow information is being transferred to the LEM domains by cutting fragments and attaching them to their neighbors. The difference now being that splicing is happening at the cluster level or the supergrid level. Using this new method known as supergrid LEM or SG-LEM, we have achieved a speed up of nearly 20 times compared to conventional LEM. It's also led to 3 publications detailing the method and validating it against experimental data. We've also identified the clustering method as being critical to correctly predicting flame behavior. This is an area of improvement for future studies. Thank you for listening to this short popular science presentation on my PhD project. This is a glimpse into what goes on into combustion simulation, and I hope you found it interesting and fun.
This was a popular science presentation from Chalmers University of Technology in Sweden.